What if I told you that your roof could generate electricity without solar panels, no batteries, no permits, no contracts, just a few dollars in simple materials, and a principle that has existed for more than 200 years? It sounds impossible, because if something this simple really worked, you would have heard about it already. But that is exactly the point. Some technologies are not forgotten because they failed. They are forgotten because they make entire systems unnecessary. Electricity that you can produce yourself is electricity that cannot be easily measured. And electricity that cannot be measured cannot be billed. That creates a problem. Not for you, but for an industry worth hundreds of billions of dollars every year. So instead of spreading, this idea slowly disappeared from books, from workshops, from public knowledge. But the physics never changed. This is the story of a system so simple that almost anyone can build it, and powerful enough to challenge the way we think about energy independence and control. The story begins in 1821 with a simple experiment that did not look important at first. A physicist took two different metal strips. One was copper, the other was bismuth. He joined them together at both ends, forming a closed loop. There were no batteries, no external power source, just metal. Then he did something unexpected. He placed one of the junctions in contact with heat, something as simple as the warmth of his own hand. The other junction remained at room temperature. Nearby, he positioned a compass. At first, nothing seemed to happen, but within moments the needle began to move. Slowly, subtly, but undeniably. A magnetic field had appeared, without any visible source of electricity. What he had just observed was a direct conversion of heat into electrical energy, not through combustion, not through chemical reaction, but through a difference in temperature. When the results were published, other laboratories across Europe repeated the experiment. The outcome was always the same. Two dissimilar metals, a temperature difference, a measurable electrical effect. The phenomenon was later named after its discoverer. Today it is known as the Seebeck effect. There was no mystery in how it worked. And that is what makes it so strange. Because the simpler a principle is, the harder it is to justify why it would ever be forgotten. No moving parts, no fuel, no complex machinery, just heat and difference. And from that difference, electricity begins to emerge. At first, the discovery remained inside laboratories. A curious effect, interesting but not yet practical. But about 80 years later, something changed. By the early 1900s, engineers began to see what others had overlooked, not just the effect itself, but where it could be used. In 1902, a simple realization emerged: roofs get hot, very hot. Under direct sunlight, metal rooftops can reach temperatures far above the surrounding air. By late afternoon, they begin to cool, and by night, they can become significantly colder. Every single day, a natural temperature cycle repeats itself. Heat, then cooling, then heat again. An endless rhythm, free, predictable, always available. And that is exactly what the thermoelectric effect needs. So instead of heating metal in a laboratory, they let the sun do the work. They connected strips of copper to galvanized iron roofing. One junction was placed where the sun hit the strongest on the surface, exposed to direct heat. The other was positioned in shade or in contact with cooler air beneath the structure. The result was a continuous temperature difference, and with it, a continuous electrical output. No fuel, no moving parts, no operator required. Small systems began appearing in rural parts of Germany, Austria, and Switzerland. Farmers far from electrical grids experimented with these setups using inexpensive, locally available materials. They were not building power plants, they were building independence. And then, something changed. Not in physics, not in the materials, but in the world around them. By the 1920s, the electrical industry was expanding at an unprecedented speed. Power lines stretched across cities, contracts were standardized, meters were installed in homes. Electricity was no longer something you produced, It was something you subscribed to. In 1923, large utility companies began consolidating control over generation and distribution. Infrastructure grew. Regulations followed. And with them, a new narrative quietly took shape. Generating your own electricity at home was no longer seen as practical. It was labeled inefficient, unreliable, even dangerous. The shift did not happen overnight. It did not need to. Books stopped mentioning small-scale thermoelectric generators. Supply catalogues no longer listed components for building them. Workshops moved on to technologies that aligned with centralized systems. The devices themselves did not stop working. They simply stopped being talked about, because the principle behind them could not be patented, it could not be owned, and most importantly, it could not be easily controlled. And when a technology cannot be controlled, it becomes difficult to integrate into an industry built on dependency. So the knowledge faded, not erased from physics, but erased from public awareness. And what remained was silence around something that had once been quietly working on rooftops across Europe. At its core, the principle behind this system is not complicated. When two different metals are connected together, and the two junctions are kept at different temperatures, something begins to happen at the microscopic level. Electrons start to move. Not because of a battery, not because of a chemical reaction, but because heat itself creates an imbalance. The hotter side has higher energy, the colder side has lower energy, and nature always tries to balance that difference. So electrons drift from one side to the other. That movement is electricity. There is no trick involved, no hidden mechanism, no secret component. Just two dissimilar metals, one hot junction, one cold junction, and a continuous flow of charge created by the temperature difference between them. This is not an experimental idea. It is a well-documented physical phenomenon taught in physics textbooks and used in modern sensors and space technology, which makes one thing very clear. The reason you have not seen this on rooftops everywhere is not because it does not work. At this point, the idea sounds convincing, but the real question is simple. How much electricity can it actually produce? A single thermoelectric pair like copper and iron, with a temperature difference of around 30 degrees Celsius, can generate a small voltage, usually just a fraction of a volt. On its own, that is not enough to power a home, not even close. And this is where most people stop. They assume that because one unit produces very little, the entire system must be useless. But that is not how this technology works, because thermoelectric systems are modular. Instead of relying on a single pair, you connect many of them together, one after another in series. Each pair adds a little more voltage to the total output. 10 pairs, 20 pairs, 50 pairs. The numbers begin to add up. With around 20 properly configured junctions, it becomes possible to reach voltage levels suitable for charging small devices, powering emergency lighting, or maintaining low-energy systems. And this is not just theory. Modern research has shown that thermoelectric arrays, when scaled across a surface, can produce measurable power per square meter, especially in environments with strong day-night temperature cycles. Which brings us back to the roof. Because most rooftops naturally experience exactly that heat during the day. Cooling at night, a repeating cycle, every single day. The key insight is this: low output does not mean no value. In modular systems, small outputs are not a limitation, they are a building block. And once you understand that, the entire concept starts to look very different. So if the physics is real, and the materials are simple, and the system can be scaled, why isn't this everywhere? The answer is not in physics, it is in economics. The modern electrical system is built on a very specific model: centralized generation, controlled distribution, and continuous billing. Power plants produce energy, grids deliver it, meters track it, and users pay for it every month. For this model to work, one condition must remain true: people must depend on the system. But thermoelectric generation does not fit that model. It does not require permission. It does not require connection to a grid. And once built, it produces electricity without ongoing cost. That creates a structural problem, because a system that anyone can build is a system that cannot be easily controlled, and a system that cannot be controlled is difficult to monetize. It is not just traditional utilities. Even modern alternatives like residential solar follow a similar pattern. Panels, inverters, batteries, installation costs, financing plans. Entire industries built around selling access to energy. But a thermoelectric setup made from basic metals does not fit into that structure. It is too simple, too cheap, too independent. You cannot patent the underlying principle. You cannot lock it behind proprietary hardware. And you cannot charge someone monthly for something they generate themselves. So instead of being developed and promoted, it was quietly ignored. Not banned, not disproven, just left out. Because sometimes the most effective way to control a technology is not to fight it, but to make sure people never think about it at all. In many parts of the world, especially across rural regions of Latin America, there is a different relationship with technology. Not everything is purchased. Not everything comes from a company. Many solutions are built. In these environments, people learn to work with what they have. Metal roofing sheets, scrap wire, shade, sunlight, airflow. Knowledge is practical, adaptable, passed from one person to another. And in that context, a system like this makes perfect sense, because it does not depend on access to advanced infrastructure. It does not require expensive components, and it does not rely on external supply chains. It simply uses what is already there. The roof is no longer just protection from the weather. It becomes an active surface, one that interacts with heat, light, and air, and with a basic understanding of thermoelectric principles, that interaction can be turned into energy. This is why the idea never fully disappeared. It survived quietly in places where independence was not a trend, but a necessity. Because at its core, this is not just a technical system. It is a way of thinking, one that sees opportunity in everyday conditions and turns limitation into self-reliance. Now, instead of just talking about the idea, let's make it real. This is a basic thermoelectric setup. It will not power your entire house, but it will prove that the principle works. And once you see it working, everything changes. The materials are simple and inexpensive copper wire, galvanized iron wire, electrical tape, and a basic multimeter. That is it. Start by cutting 2 pieces of wire, 1 copper, 1 iron, each about the same length. Take one end of both wires and twist them tightly together. This point will become your hot junction. Now place that junction on the hottest part of your roof. A spot exposed to direct sunlight is ideal. Next, separate the other ends of the wires. These will form your cold junction. Position them in a cooler area under shade, inside airflow, or even slightly beneath the roof, where temperatures are lower. Make sure the 2 ends do not touch each other. Now connect your multimeter. Set it to measure DC voltage. Attach one probe to the free end of the copper wire, the other probe to the free end of the iron wire. Wait. As the temperature difference builds, you should begin to see a voltage reading. It may be small, but it will be there. And that is the key moment, because now you are not just hearing about the effect, you are seeing it. To increase the voltage, repeat the process and connect multiple pairs in series. Each additional junction adds to the total output. What you are building is not just a device, it is a system that scales with your understanding. At this point, you might be wondering why this isn't already powering everything. And the answer comes down to one critical factor: temperature difference. Not the type of metal, not the length of the wire, but how well you can maintain a gap between hot and cold. Because the moment that difference starts to shrink, the voltage drops. If the cold side warms up, the system weakens. If the hot side is not exposed to strong sunlight, output decreases. Everything depends on how effectively you manage heat. This is where design begins to matter. The position of your roof, the angle towards the sun, the presence of shade, airflow across the surface. even how firmly the junction is attached to the metal. A junction placed in direct, stable sunlight will perform better than one exposed to shifting shadows. A cold junction placed in moving air will stay cooler than one trapped in still heat. Time of day also plays a role. Midday produces the strongest temperature differences. Early morning and late evening create smaller outputs, but still measurable ones. Different roofing materials behave differently as well. Some absorb and release heat faster than others. This is not a trick. It is a system that responds directly to real-world conditions. And the better you understand those conditions, the better the system performs. In a remote area near Oaxaca, Mexico, a camper decided to test this idea for himself. He did not have access to a power grid, no solar system, no generator. So he built a small thermoelectric array using what he had. About 30 pairs of copper and iron wire, mounted across the surface of a metal roof. Each junction carefully placed, some exposed to direct sunlight, others positioned in shaded airflow to maintain a temperature difference. The setup was simple, almost improvised, but it worked. Not at a massive scale, not enough to power appliances or large devices, but enough to do something important. It powered small LED lights at night, it kept a radio charged for emergencies, and it did this consistently, day after day, without fuel, without noise, without cost. Over 2 years the system remained in use. No contracts, no meter, no monthly bill, just a direct application of physics, quietly doing its job. And for him, that was enough. Because the value was not just in the electricity, it was in the independence. At first it looks like a small idea, a few wires, a bit of heat, a tiny voltage. But the deeper you look, the bigger it becomes. Because this is not just about electricity. It is about how we think. A roof is no longer just a barrier against rain. It becomes an active surface interacting with sunlight, air, and temperature. Heat is no longer a problem to escape from. It becomes a resource. And energy is no longer something you only receive. It becomes something you can create. Not at an industrial scale. Not all at once, but step by step. Understanding comes first. Then experimentation, then expansion. Every large system begins this way. What matters is not how much you generate on the first day. What matters is that you realize it is possible. Because once you see it working with your own eyes, something changes. The idea that energy must always come from outside, from companies, contracts, and monthly bills starts to break apart. And in its place, a different perspective begins to form. One based on knowledge, on observation, on self-reliance. This technology was never lost. It was simply left out, waiting for someone to look at something ordinary and ask a different question. If this kind of hidden knowledge interests you, subscribe, share, and keep exploring. Because sometimes the line between dependence and independence is nothing more than a principle that was never meant to disappear.